In this video, we will go over the calculation of first derivatives using the finite difference approximation. To accomplish this, we will use the following definition, which is based on the Taylor series. Using a function f, we will evaluate this function at a point x plus some delta x step size. Here, x represents our point of interest, that is, the point where we want to evaluate our first derivative, and delta x is the step size, or a distance separating our point of interest x and a reference, which it just so happens to be a point in front of it. Now, recall that a Taylor series is an infinite process. As such, we must truncate it. We choose to do this right after the second derivative. We can then rewrite our function combining all those higher order terms into what is known as the big O notation. We then proceed to simplify our equation. This is accomplished by dividing both sides of our equation by delta x. Which will also reduce the order of the delta x next to the big O notation. It is important to notice that the error, in this case given by the second order element, is proportional to delta x of the first power. This is very useful in understanding why reducing delta x will reduce the error given by the truncation. Do keep in mind that making delta x too small will increase the round of error. We can then combine the error with the higher order term to obtain the final equation in the following form. This is what we know as the forward finite difference. Following the same idea, we will use the same definition of the Taylor series that was introduced before. However, this time we will use a function f, evaluated at a point of interest x minus a delta x step size. This will change some of the sign, but it should look very similar as our previous definition. I should point out that I made a mistake when writing the second derivative, but I will go back and fix it in just a minute. Once again, we truncate the infinite process right after the second order. We then obtain the following form. The simplification process goes the same as before, but the only difference is that this time we will divide by a negative delta x, such that we obtain the following. We can then solve for f prime just as we did before. Also, it is very important to see that the error is, once again, proportional to delta x. At this point, we can write the final form of our function. This is what we know as the backward finite difference. Finally, we take the Taylor series definition from forward finite difference and subtract it from the Taylor series definition of the backward finite difference. This sounds a little complicated, so let me begin by writing down the first Taylor series definition we used. That of f as a function of x plus delta x. In the same way, I will write down the second Taylor series definition we used. That one of f as a function of x minus delta x. As we saw before, we will truncate this infinite series right after the second derivative. We will do this for both definitions. Carrying out the subtraction, we obtain We then simplify the resulting equation by dividing both sides by 2 times delta x. As a final step, we solve for f prime, which will yield the final form of our equation. This is what we know as the central finite difference. A peculiar thing to note is that the error in this case is proportional to delta x squared. This is different than forward and backward different, for which the error was proportional to delta x. This concludes the finite difference approximation of the first derivatives.